Now, for you to get a pretty good feeling for the density operators, it's always a good idea to look at a few examples. And of course, there's no better system to go for than just our good old Qubit. So let's say we are given a qubit in state psi, which is alpha 0 plus beta 1. So what's the density operator associated with this qubit? It's a pure state, but we know that in this case the density operator rho will be the projector on this state, which we can write as alpha 0 plus beta 1. And here we have alpha complex conjugate 0 plus beta complex conjugate 1. So then you can see that this is equal to alpha mod squared projector on 0 plus beta mod squared projector on 1 plus then we have alpha beta complex conjugate 0 1 plus complex conjugate of that, so it will be alpha star beta 1 0. Okay, so that's our density operator. You can also write it in a matrix form. So if you write it in the computational basis in the matrix form, then on your diagonal you will have alpha mod square. So this is this term here. Here you will have beta mod square. So this is this term. And then you have alpha beta complex conjugate and alpha complex conjugate beta. So this is the matrix representation of the density operator associated with this particular pure state. So for some historical reasons, perhaps because density matrices were quite popular with people working on atomic physics, the diagonal elements of density operators or density matrices, so once we fix the basis, we are talking about matrices, right? So the diagonal elements of density matrices are called populations. Off-diagonal elements quite often are called coherences. So any physical process, for example, which kills the off-diagonal elements, you see, if I just reduce the off-diagonal elements or even make them zero, it's still a valid density operator. But that kind of process where you destroy coherences is called decoherence. We will use decoherence in kind of a broader sense, but the origin of the term decoherence comes from destroying coherences of density matrices. So for example, if I take a state, one of the, say, the eigenstate of the Pauli X, which we quite often write as plus, say, 1 over square root of 2, 0. I'll consider the two eigenstates of the X operator. Then the corresponding density matrix you can see right away will be equal to half. It will have terms 1, 1, plus minus 1, plus minus 1. So those are just simple example of density matrices associated with pure states of the qubit. But of course, there are states which are not pure states. Pure meaning you can describe the state using the state vector. Pure meaning also that your density operator essentially is a projector on that state. But as I mentioned, in general we can have density matrices which, for example, this off-diagonal element here can be reduced to 0, in which case, so let's make it 0. So if it is 0, then the corresponding density operator is alpha. If the off-diagonal elements are 0, then you can write this density matrix as alpha mod square projector on 0 plus beta mod square projector on 1. You can see that obviously the trace, the sum of the diagonal elements is equal to 1, simply because alpha mod square and beta mod square, as you can see from this expression here, are the probabilities that if you were to measure the state in computational basis, those are the probabilities that you get 0 or 1. Now, given that any matrix in a 2x2 matrix can be decomposed in terms of the Pauli basis, there is a very convenient way of parametrizing density operator on a qubit. Any density operator rho can be written as half 1 plus Sx sigma x plus Sy sigma y plus Sz sigma z. It's quite often physicists write it as half 1 plus vector S and vector sigma. So it's like a scalar product of a Euclidean vector with components Sx, Sy, Sz, and a vector made out of the sigma operator, sigma x, sigma y, and sigma z. And this is actually another way of introducing the Bloch vector. So if we now consider the Bloch sphere, that you should remember how we represented quantum states of individual qubit. Now there's a nice way to generalize it to states which are described by density operators, but not necessarily by state vectors. So if you have the Bloch sphere, which actually is a Bloch ball, because now we will be also interested in what's inside, then this vector S now is parametrizing nicely any density operator on a qubit. So any 2x2 density matrix can be parametrized in terms of the Bloch vector using the Pauli basis. So we simply decompose it in the Pauli basis. So if you want to see it as a matrix, so that looks like this. So it's this factor half, and it's on the diagonal will be 1 plus Sz, 1 minus Sz, Sx minus Sy, and Sx plus Isy. So you take any Hermitian matrix, and if you can just write it in this form, then you can see right away what are the components of the Bloch vector. Now the Bloch vector can be just anything from any point inside the Bloch sphere, and including the points on the surface of the sphere. So the length of the Bloch vector in this case can well, all the points here on the surface will have the length of the Bloch vector would be equal to 1. And but you can also look at the point which is right in the middle. So the length of the Bloch vector here is equal to 0, and that particular state is you can see that if you put s equal to 0, the corresponding density operator is proportional to the identity. So this point here gives you the density corresponds to the density operator half the identity. So that's called a maximally mixed state. So that is the state where that is a rather peculiar state, which basically is carrying no information about the object. We will just look at those states in a moment. So pure states on the surface of the Bloch sphere, just right in the center is a maximally mixed state, and then any single point within the Bloch sphere gives you a density operator of a qubit. This is a very convenient parametrization. It's sort of like a way of generalizing the concept of the Bloch vector that we had before. In the past, well, in our previous lectures, we were talking only about the Bloch vectors, which were on the surface, and we introduced them in a different way. But now it just nicely, you go to the Pauli basis, you get the Bloch vector as the components of your density operator in the Pauli basis. Quite convenient. We will use this visual image of a density operator of a qubit. Unfortunately, it doesn't work in higher dimensions, so qubit is rather special. It just it admits this beautiful geometric representation of its states and its evolution, as you will see later on. Unitary operations are still rotations of the whole Bloch sphere, so you will just see immediately how density operators associated with qubits evolve. They're just under the unitary operations they are simply rotated with a Bloch sphere. But of course, soon we will be talking about some other operations which are induced on density operators by the unitary dynamics of the whole system. But when we look at the subsystem, it's going to evolve in a non-unitary way. So then those Bloch vectors, if it is a qubit, then those Bloch vectors will be squeezed or expanded or shifted in some other directions. So very interesting and very useful picture to have in mind for density operators associated with qubits.